Hello, welcome to Hitman 3. I want to take a look at these railings for a moment. And what's interesting about them is that they are a 2D texture. We can really see that where these railings meet the top railing. The top railing is a 3D object, but these railings that we see on the middle and lower half of the screen are just a 2D texture. There's a 2D image file somewhere in the game's data that contains a pixelated image that keeps track of what pixels are filled in, and then they also keep track of some information about the kind of the what this would be in 3D if it had a 3D geometry, so that we can light it as if it were 3D, and that gives it a very 3D look to it. But we can really see, if we look closely at this texture, we can really see a pixelated effect going on here. This kind of stair stepping, right, where every time you go like one unit over, it looks like it goes 2 units or maybe 3 units down, and then 1 unit over, and then 2 or 3 units down. And you can see this throughout this texture. And this is quite common, these strange blobby edges. They're not sharp, crisp, pixely edges. That would actually look very strange in this particular game. It's used as a pixelated art style for some video games, and it works really well if that's part of the art style that you're going for in your video game. But in this game, it would look a little bit weird if everything, or if a few things were pixely, but not everything was pixely. Um, so instead, we see these rounded edges, and I was kind of curious, where are those rounded edges coming from? So in this video, I'd like to show you my exploration into what's causing not just the pixelated effect, the pixelated stair-stepping effect, but also what causes the roundedness of this pixelated stair-stepping effect. And so I hope you'll join me for this exploration into how transparency works in video game textures. So in order to be able to make sense of what's going on in our video games, we need to take a look at how 3D rendering is accomplished in video games. So suppose I have some sort of square, and video games don't actually work with squares, they work with triangles, but let's assume that we're working with a square for a moment just because it's going to make it easier to think about textures because textures are squares. So we have some sort of square, and what we want to do is we want to work out where on the screen to draw the various vertices of the square. And the way we do this is very similar to the way that an artist might. Artists will, when they're trying to draw a landscape, they might set up some sort of grid in front of them on an easel or something, and then use that to copy individual, like what's going on in this square of the grid, what's going on in this square of the grid, what's going on in this square of the grid, from their view of the landscape onto a grid that they have lightly sketched onto the canvas. And something like that happens in video games as well. We have some sort of grid. This is the screen, and we have our camera, that is the eye of the painter. And what the computer will do is it will take each vertex of this square and trace it back, trace a line from there to the camera, and see where it intersects this grid plane that we're using as reference to set up our scene. And by tracing back to figure out where these points wind up here, we get a perspectively correct view of the original square. And we can just copy this from the virtual space of our scene onto our screen. And then we'll have an image of this square that's been distorted a little bit by perspective on our computer screen. Suppose now that we wanted to draw some sort of texture on this plane. Say we wanted to draw an image of a tree. So here we have our image of the tree, and what we actually want to do is kind of like ray tracing. What we want to do is we want to go through pixel by pixel. Remember that this plane here represents the screen of our computer, and what we want to do is go pixel by pixel. So um, and just for the pixels that represent the square while we're working on the square. If we're working on something else, we'll use other pixels, but just the pixels that correspond to this square here, we'll go pixel by pixel, trace the ray of light back to the original texture source, and try to figure out what color to color the pixel based on where it came from. So suppose that we want to figure out what color to color this pixel here. Well, we trace it back from the camera until we hit the image, and we see that, oh, that we've hit the leaves, so maybe there's like a green pixel here that we want to sample and use that as the color of this pixel. There's one slight problem though. When you're doing this sort of math, it's hardly ever the case that you're going to hit a pixel of the texture dead on. You're probably going to hit somewhere between a bunch of other pixels. And so what the computer has to decide is, if we hit this image somewhere in between pixels, how do we decide what color to color this particular pixel on the screen? And there's many options. There's nearest neighbor, there's bilinear, or sometimes you'll see this called trilinear. There's some anisotropic stuff. And there's also, you can also do bicubic or tricubic, which is a bit more complicated. In this video, I'm going to be focusing on bilinear, or everything that I'm saying for bilinear also applies for trilinear, and actually also some other sorts of pixel interpolation techniques as well. But I'm going to be focusing on bilinear because that's really the simplest thing that really showcases this effect that I'm trying to talk about. So what is this effect? Well, imagine that we've zoomed in on this point here of the image. So the image that we're looking at specifies the color of a grid of points, right? It tells us if we are looking exactly at this position of this texture, it's going to be exactly this color, right? That's because our texture image is built up out of a grid of pixels, and it has specified the color of each pixel in that grid. But again, we have this issue that when we send our ray of light backwards to try to see where it came from on this texture, maybe it didn't come from one of these points on the grid. Maybe, and most likely, it came from somewhere in between. So we need to figure out what color to color this point here, and we're going to do it based on the colors of these 4 points here. So one option we could pick is to use the nearest neighbor, right? So in this case, we should color this pixel the same color, exactly the same color as this pixel here, the nearest neighbor to that pixel. And what this produces is a pixelated effect, where each of the 4 quadrants of this square wind up getting exactly the color of the corner that they're closest to. And so what you'll see is that this quadrant, and actually this entire square here, winds up getting colored the color of this pixel. This entire square here gets colored the color of this pixel. This entire square here gets colored the color of this pixel. And this entire square here gets colored the color of this pixel. And that produces a pixely effect. When we look at this texture, it will look pixely. Cloud Gardens, for instance, uses nearest neighbor interpolation to produce this 3D pixel art effect. All of the pixels in this square here of this texture are colored exactly the color of the nearest pixel in the texture image file for this particular piece of material. And so they all have the same color. There's no interpolation between them. And then once we get closer to another pixel, then the color suddenly changes from one to another. But this is typically not how you want to work with textures in a lot of video games. Unless you're going for a pixelated effect, you probably want something else. You probably want to blend these colors together. And the way that this blending typically works is by linear interpolation. What bilinear interpolation does is it interpolates along the grid edges in a linear fashion between two colors. So every point along this grid edge, we know what color it should be. It should be a linear interpolation, a smooth gradient between the color of this pixel and the color of this pixel. And similarly, down here, all of the points on this particular grid line should be a smooth gradient between this pixel color and this pixel color. So what that means is that we know what the color should be here and what the color should be down here. And to determine what the color should be at our point, we linearly interpolate between the color of this point and the color of this point. And it's very fortunate, right? We wouldn't want to use this technique if it somehow had an effect that allowed us to tell the difference between vertical and horizontal. It turns out that if instead you do your interpolation the other way, if we interpolated between the color of this pixel and the color of this pixel, and then interpolated between the color of this pixel and the color of this pixel, and then we know what the color of this pixel is, we know what the color of this pixel is, and we set up a gradient of colors between them. If we got different answers depending on if we started out going horizontal and then go vertical, or if we started out going vertical and then go horizontal, it wouldn't be a particularly compelling way of interpolating textures. But it turns out that the order that you do this in, if you work out the math, the order that you do this in doesn't matter. And that's absolutely fantastic. So there's no distinct, like you can't look at a texture that's been interpolated and tell this is vertical and this is horizontal. Although you still can tell, well, this is either vertical or horizontal and this is either vertical or horizontal. Here in Walden the video game, it's much harder to see the individual pixels of a texture. We have to get our camera very close to the texture. If you look at the faraway leaves, you really can't see the underlying pixels of that texture. You really have to look very closely. And even then, because of the blurring effect of these gradients, of these linear interpolations between colors, it doesn't stand out nearly as much, the underlying pixels of the texture. But we can, if we look carefully, we can see the pixels that make up this texture file, and we can see how the colors have been interpolated in the horizontal and vertical directions in this image. But this isn't the full picture. In addition to interpolating the red, green, and blue values of each pixel, we also interpolate the alpha values of those pixels. Alpha represents the transparency or opacity of a pixel. An alpha value of 1 or 255, whatever the maximum value on the scale is, represents a pixel that is entirely opaque. That is, we can see it and we can't see through it. And an alpha value of 0 represents a pixel that is entirely transparent. We can't see it and we can see through it. And alpha values in between represent pixels that we can see and we can also see through, and we have to blend those colors together. Well, it turns out that this is actually really complicated in terms of rendering, because in order to work out exactly what the right color for a pixel is, we need to keep track of every single transparent layer that a ray of light kind of tracing out for that pixel would pass through before it finally hits an opaque object. So we have to keep track of a lot of different things, and it may not be the case that the order that these things are presented in is the order that the light will pass through them. They might be stored in a different order in the computer's memory, and then we're going to have to sort them, and we have to sort them per pixel because some of them might be at angles to each other. It's a very complicated process, and there are certain algorithms and tricks for making this process easier, so you will see more and more translucency, that is alpha values strictly between 0 and 1. You'll see those more and more in video games nowadays, but it is still quite complicated, and a lot of video games just don't want to bother with this added complexity. And so what they do is they say, instead of dealing with pixels that are going to be partially transparent, every pixel is either going to be completely opaque, completely there, or completely transparent. And the way that they do this is by looking at the alpha values that are presented to them and saying, if the alpha value is above a certain threshold, then this pixel is opaque. And if the alpha value is below a certain threshold, then this pixel is transparent. For instance, on a scale of 0 to 1, we might say that any pixel with an alpha value larger than 0.1, 1/10, we'll say is opaque, and anything less is transparent. So let's work out some equations to see what sort of shape that gives us when we look at that sort of inequality. So suppose that we have enlarged our square between pixels, and the alpha values of these 4 pixels are A, B, C, and D respectively. And we're interested in working out what color to color a particular pixel here at coordinates X and Y. And as is tradition, we will measure Y from the top. This is kind of a strange thing about computer graphics. I believe that this goes all the way back to the days of text terminals, measuring Y from the top downwards as opposed to from the bottom upwards like we do in mathematics. This leads to all sorts of confusion, but we'll measure it this way in this video. So the alpha value for this pixel here is going to be a weighted average between the alpha values of this pixel and this pixel. That is some appropriate average of A and B. And in particular, that average is just going to be 1 minus x times A plus x times B. Notice that this is an affine combination. It is a weighted average between A and B. That is a linear combination where the coefficients add up to 1. And we can see when we plug in x is equal to 0 into this formula, we get 1a plus 0b. So when x is equal to 0, we're here and we get an alpha value of a. And when we plug in x is equal to 1 into this formula, we wind up getting 0a plus 1b. And so at this point, the alpha value will be b, so that matches with what we expect, and this is a linear formula in x. So this is a linear interpolation between a and b. Similarly, down here, the alpha value of this pixel is going to be 1 minus x times c plus x times d. And it's important to note that this isn't special. There isn't anything special about the alpha value. This is also how the R, G, and B values, the red, green, and blue values, are being interpolated between these pixels as well. It's just that it's the alpha value that's going to be causing our unusual edges when we do alpha thresholding. So finally, let's interpolate between this pixel and this pixel, and that's going to give us 1 minus y times the color of this pixel plus y times the alpha value of this pixel. So this is a very complicated formula, and if we expand this out, what we're ultimately going to get is some sort of polynomial that looks like this. P plus qx plus ry plus xsy. It doesn't really matter what these constants are, just that you can adjust them. These constants reflect the alpha values of these four corners. But for the purposes of this video, it doesn't actually matter if we work out what these coefficients are. They just depend on A, B, C, and D. And so this is the alpha value of this particular pixel here. And the thing that really surprised me when I worked out this formula is that there's this xy term here. And remember that the inequality that we're solving when this value is larger than some threshold. For instance, 0.1, if we're measuring our alpha from 0 to 1. So we have this sort of inequality, and well, what does this region look like? Well, let's look at its boundary. Boundary is going to be when this is equal to 1, and it turns out that shape is usually a hyperbola. So here I've plugged in the formula that we worked out on the board into GeoGebra's 3D grapher, and we can see the formula here. Z is going to be the alpha value, and we're going to plot these values across the square where x goes from 0 to 1 and y goes from 0 to 1. This is the square that we saw up on the board. And when we plot this, the shape that we see is a hyperbolic saddle. Nonetheless, when we take cross sections, let's say we take cross sections vertically through the square from the top to the bottom, we notice that these cross sections are linear. They're lines, that we have linearly interpolated the alpha values from the bottom to the top of the square. And regardless of what vertical cross-section we take, we wind up seeing a line. The key thing is, though, that unlike if we were taking cross-sections of a plane, the slopes of these lines can change. The same thing if we wind up taking cross-sections across the square, cross-sections with a fixed value of y. We see that each of these is linear. We are linearly interpolating the value of alpha across the square. However, because we have this hyperbolic shape, when we wind up taking cross-sections vertically, cross-sections for fixed values of z, we're going to wind up with hyperbolic shapes. And what this corresponds to is having a particular threshold for alpha. So we see here in red, I've marked the values, the points where alpha is above the threshold, in this case of 0.3, and in green, this plane that we're drawing breaks through the surface of the curve, and so we see these pixels where the alpha value is less than 0.3 as being this cyan color. And here we can really see the hyperbolas very distinctly as the boundary between these two regions. And at some point it switches over, so here we are back in Hitman 3, and we now know that these particular curved shapes that we're seeing are caused by pixels in the underlying texture of this file. So some of the pixels have been marked as completely opaque. Those are the ones that we see here. And some of the pixels have been marked as completely transparent. And at the edge between the two, the computer is bilinearly interpolating that alpha value, and we're seeing just the pixels with alpha value above a certain threshold. And that's causing these hyperbolas at the edge of these pixels. And you can use this to tell a lot about how a particular effect is being implemented. Here we see the hyperbolas, and we can tell that this effect has been caused by something involving alpha thresholding. On the other hand, if we take a look at this texture, we don't see the kind of hyperbolic edges between these same metal railings and the background behind them. The metal railing and the background are part of the same texture file, and each pixel is being bilinearly interpolated, including those pixels on the edge. On the other hand, if we take a look at this particular texture, we can see the rounded edges that are characteristic of alpha thresholding. And this suggests that this is actually two separate textures, that the gold leaves are one texture with transparency on top of the background, which is the material for the overall surface. So by understanding the mathematics behind alpha thresholding and what sorts of effects it gives us, this can actually give us a glimpse into how video games have implemented various effects that we see. So thank you for joining me on this rather unusual adventure through various video games and how graphics is implemented, and I hope you'll join me in a future video.